Alright, so in this problem, it tells us that the scatter plot to our right shows the relationship between latitude and the mean July temperature for 12 cities in the United States. The equation of the regression line relating these variables is y hat is equal to 106.5 minus 0.782x. Alright, now just so that we have more context, some of us may have forgotten what we learned about latitude in our during our younger years. So as a brief recap, when we look at the globe, right, we have the equator, and the equator is going to be our baseline, which has a latitude of 0 degrees. Right, and as we go higher and higher up, each one of these horizontal cross sections is going to have a greater degree latitude. All right, so this dashed line right here, that's the Tropic of Cancer. It's got its degrees latitude is 23 degrees in 26 minutes, so it's a little bit greater than 23 degrees. Then we have a really high latitude way up here, which has 66 degrees. In between, we're going to have these other latitude lines that might be like 30 and 40 and so on. Right, we have the latitudes of 12 cities, and we also have mapped the temperatures, the mean July temperatures of those 12 cities. We can see that latitude is on the x-axis, so that's going to be our explanatory variable. It's on the x-axis, it's our explanatory variable. Mean July temperature is going to be our response variable. And so our predicted mean July temperature is equal to 106.5 minus 0.782 times the degree latitude of that city. All right, so let's look at A. It says predict the mean July temperature in Fairbanks, Alaska, which has a latitude of 65 degrees. Right, so that's going to be simple enough. It's just going to be 106.5 minus 0.782 times that latitude, which is 65 degrees, and that gives us a predicted July temperature of 55.67 degrees. Now the next part is critical. It says how confident are you in this prediction, and explain. So we're actually not going to be confident. The reason is that because the equation is derived from these 12 cities. These 12 cities give the data that we use to derive this equation right over here. Now the latitudes of these 12 cities have a minimum of 29 degrees and a maximum of 42 degrees. That means that that regression equation that we derived is only valid for locations with latitudes between 29 and 42 degrees. But Fairbanks, Alaska has a latitude of 65 degrees, which means that we can no longer validly use this equation to make predictions about the temperature of Fairbanks, Alaska. Let me give you a really good example / explanation of why we can't extend or extrapolate this equation to cities that have latitudes that are either less than 29 degrees or greater than 42 degrees. So this graph right here represents what's known as the Yerkes-Dodson law. What the Yerkes-Dodson law says is that the relationship between arousal and performance takes on this inverse U relationship. This is like an upside down U, meaning that when your arousal is really low, your performance isn't going to be that good. Right? If you're not really taking it seriously, if you're not really focused, then your performance isn't going to be very good. As your arousal increases, as you're increasing your attention and your interest in what's going on, those increases in arousal will, up to a point, be matched by an increase in performance. All right, and it reaches this optimal level. Now, once arousal gets even higher than this, what happens is your performance then will begin to decrease, because at that point you're getting heavier and heavier anxiety, and that anxiety is impairing your performance. All right, you're too anxious to be able to think straight. You're too worried to be able to think straight, and so it's going to have negative effects on your performance. All right, so let's use quantitative variables to replace these. So instead of arousal, we could measure arousal, say, in your heart rate, your beats per minute, with relatively low, we'll just say 90, and high being 150. And for performance, we can do grades. All right, a low grade is going to be a 50, a high grade is going to be a 100. Right. Now, let's say that I take data on people in my class and see how their heart rate corresponds to the grade that they make on their test. But here's the critical thing. Nobody in my study has a heart rate greater than 120. All the people in my study have a heart rate between 90 and 120. So we're only going to have this left half of this graph then, essentially. And so if I were to derive a regression equation from the students in my study, that regression equation might look like this. Y hat, or the predicted grade, is equal to negative 100 plus 1.67 times the explanatory variable, which is going to be our heart rate. All right. This regression equation is going to fit perfectly with my students in my study. Remember, I only had students who had heart rates between 90 and 120. So for example, if I plug in a heart rate of 90 beats per minute, then the predicted grade is a 50.3, just as we see on the graph. If they, the predicted grade for a person with a heart rate of 105 beats per minute is going to be a 75.4. Again, that corresponds pretty well with what we see here. Okay, if they have a heart rate of 120, their predicted grade is going to be just about 100. All right, fits perfect. Can you hold on just a second? All right, sorry about that. Okay, so far, this regression equation that we have seems to fit perfectly with this line. All right, and it seems to do exactly what we would expect it to do. But remember that I derived this regression just from students who had heart rates as low as 90 and as high as 120. What if we apply this regression equation to a student who had a heart rate of 135? Now we know from when we saw this full figure that it's actually supposed to get lower than 100 at this point. Once you have a heart rate of 135, at that point you're experiencing too much anxiety, and it's going to impair your performance. But I didn't have any students like this in my study to take into account when I derived this regression equation. So I'm not going to be able to use that kind of data when I made this regression equation. So instead, when I plug that in, what do I get? An expected grade of 125 or 126. So what happened? I took a trend from students who had heart rates between 90 and 120 beats per minute. That gave me this regression equation. Then I extrapolated it to predict the grades of a student who had a grade outside of this range. And once I did that, the regression equation no longer worked. It broke down. That's why you never want to use a regression equation. You never want to extrapolate it to a person whose x value is outside of the range of the x values that were used to generate the regression equation to begin with. All right, Let's look at B. It says Los Angeles, California is at a latitude of 34 degrees and has a mean July temperature of 74 degrees. Calculate the residual. So before we can calculate the residual, we got to find what the predicted July temperature of LA, California is. This 74 degrees isn't what's predicted, it's the actual, the true temperature of LA, California. To find what we would predict using this equation, though, we got to plug in that 34 degree latitude in for this x. So we would get 106.5 minus 0.782 times 34. When we do that, we get a predicted temperature of 79.9. So the predicted temperature actually is close to the actual temperature, so that kind of does show our regression equation working. Now let's go ahead and calculate the residual. One last thing before I do that. Notice that the latitude 34 degrees is within the range that we have here. It is between 30 and 42, so that's why it actually is valid to use this regression equation for LA, California. All right, that's what I was just talking about on the last slide. Okay, so LA, California, latitude of 34 degrees, its predicted temp is therefore 79.9. We want to find the residual. The residual is just going to be the actual temperature minus the predicted temperature. The actual temperature was 74, and the predicted temperature was 79.9. So our residual is going to be negative 5.9. One way to remember whether it's actual minus predicted or predicted minus actual, what comes first, A or P? A comes first in the alphabet, so we do actual minus predicted. A before P, actual before predicted. So we're asked to interpret the slope of the regression line. I think I already kind of screwed this up. So here's this is the slope right here, negative 0.782. And so what that means is that for every 1 degree increase in latitude, the predicted temperature decreases by 0.782 degrees. If this had been a plus 0.782 instead of a minus, then it would be for every 1 degree increase in latitude, the predicted temperature increases by 0.782 degrees. Okay. Lastly, part D, it says, does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why. So yes, the y-intercept does have meaning in this context. The y-intercept is the predicted y value, all right, so the predicted July temperature when the x value, or latitude, is 0 degrees. So the latitude is 0 degrees at the equator. And so what is the predicted mean July temperature at any location on the equator? It's going to be this right here. It's going to be just under 85 degrees. All right. So that's going to be the y-intercept. Hold on. I'm sorry. No, this is not the y-intercept. Because right here, this corresponds to like 28. We got to see when the latitude is 0, not when it's 28. So when it's 0, the predicted July temperature is going to be this 106.5. Remember that this is the y-intercept, and then the slope is going to be the number right before x. All right, so the y-intercept has meaning when the x value can actually realistically be 0, and you can have a latitude of 0 degrees. That's just going to be any location that's along the equator.